in example 2 yesterday, we found the critical values of our polynomial, and we said that a function can only change from increasing to decreasing or vice versa at a critical value. And the only critical values we had were where the derivative was 0. They were nice horizontal tangent lines. So what we want to do then, or what we did yesterday, is we tested then between the critical values. And by testing, that means we're looking at strictly the sign, just the sign of f prime. If those are the only places where it can change at the critical values, then the sign should be the same everywhere in between them. So we made this little number line chart. We have x in the top row, f prime in the bottom row, and the line itself that defines the rows is the number line. So you put your 0 critical value and 1 critical value on the number line in order, and you pick any value from those intervals. We chose nice numbers here. Then you're interested in the sign of f prime, so you plug them back into, preferably, right, your full-fledged factored version of the derivative. And then when you were done, everywhere where you had a positive number, that meant that you had an increasing function, and a negative number meant the function was decreasing. You do want to be careful when you're writing your arguments or your answers to use your critical values, because it's real easy to say something like the function is increasing from negative infinity up to -1, because you're looking at your test value instead of what? Your critical values. That's why I always write my critical values and possible what else goes in this chart. Discontinuities. We didn't have any here. I always write them kind of up a little bit higher. Maybe circle them, highlight them, whatever. Make sure they stand out. So we were saying also yesterday that there's one other thing we could do here. We can actually use this chart not only to determine where the function's increasing, decreasing, but if you kind of draw what's happening, horizontal tangent, increasing on the left, decreasing on the right, you could also then say that our function f has a local what at x equals 0? Max. And because our function f changes from decreasing to increasing, because f prime changed from negative to positive at 1, our function has a local what at 1? Min. Okay, so that's what we're going to start with today. It's called the first derivative test. And what it does is it uses information about the first derivative on either side of a critical value to determine if that critical value is the location of a local max or a local min. So here we go. This is the first derivative test. And what is it a test for? It's a test for relative extrema for continuous functions. If you have a non-continuous function, this doesn't work. Okay? Let x equal c be a critical value. So assuming we have our critical values in hand, those are the values in the domain of f where the derivative is 0 or undefined. If we then have f prime, the derivative, changing from negative to positive at that moment, then f has to have a relative minimum there. And if f prime changes from positive to negative at that moment, then the function f has a relative or a local maximum there. If f prime happens to be positive or negative on both sides, still a critical value, but not going to be a local max or a local min. Now, let's do the visualization first, okay? Here's a critical value at c. We have a horizontal tangent line. The derivative is positive to the left and negative to the right. So since f prime changes from positive to negative at c, f has a local max at c. Here at c, we have a critical value, a horizontal tangent. F prime changes from negative to positive at c, so f has a local min there. Here's a critical value at c, but notice f prime is positive on both sides. There's no local max nor local min. It's just a stationary point, we call it. Same thing here. Horizontal tangent line, but f prime is now negative on both sides. No local max, no local min. It could also work if you have a critical value like the opposite value of x, right? As long as it's continuous. F prime would change from negative to positive, and you'd have a local minimum there. Now, what is super important, look at this note down here. What's super important when you're justifying a local extrema using the first derivative argument, you must talk about a sign change in f prime at that value of x. You can't just say, for instance, f has a local, let's say here, you can't say f has a local max at c since f goes from increasing to decreasing at c. That wouldn't be wrong, but it's not using first derivative information. So rather than saying that, you would just say since f prime changes from positive to negative at x equals c. Okay? Ready to try it out with our new purple equation that we're going to pretend has always been there? Yeah. Here it is. Example 3. If f of x equals 2x to the fourth plus 7x cubed minus 4x squared plus 3, find the open intervals, first of all, on which the function is increasing or decreasing. So example 3 essentially will be like your second question tomorrow on the exam. I'll ask you for intervals of increasing, decreasing, and then we're going to reuse the chart. Did I say exam? I meant, pop quiz that you know about. Yeah. Okay. So a function can only change from increasing to decreasing at either critical values or what? Discontinuities. We have a polynomial. Are there any discontinuities? No. But are there any critical values? Hopefully, if I reinvented this equation correctly. So we take the derivative, and we get 8x cubed plus 21x squared minus 8x plus 0. Oh. Is that right? Is it ever undefined? No. So all we need to do is set it equal to 0. Find those critical values. The first rule of factoring. Pull out a common factor of x, right? And that gives us 8x squared plus 21x. I don't think this is going to work. What happened? Oh, we could. You want to? You want to keep it going? I like that. Does it even work? Let's try it. So we know the first factor is x equals 0. And the second factor would be, let's see, x would equal the opposite of b, plus or minus the square root of b squared, minus 4 times a times c. Is that even going to work? Yeah, all over 2 times a, that's 16. What is that going to give us? Not a fun number. Anyone leave a Bubba keg up here? Oh, it was on the floor. Okay. The square root of 177. So negative 21 plus or minus the square root of 177 all over 16. So the square root of 177 is approximately what? 13? Does anyone have it? Let's call it 13.3, okay? Just for the sake of argument, over 16. Dang it, this didn't work, but hey, quadratic formula. So you're going to have negative 21 plus 13.3. You got the two decimals? Negative 21 plus 13.3 all over 16. And those come out to be what, Waldman? What? Okay, cool. So, nice. Let's say that we were able to factor it. This would factor into x times x minus each of those roots. So x plus 2.963. This is what I intended. So we'll salvage it, and I'll reinvent the question. X minus 0.337. That's what the derivative or factored would look like. So assuming that it factored into nice integers, which on your quiz tomorrow I will make sure that it works, then you would just be able to look at that and say, oh, my zeros are what? 0, negative 2.963, and positive 0.332. So what we need to do now is find the intervals. So we got x and f prime, and we're going to have 0. We're going to have negative 2.963 and positive 0.337. And now we pick our favorite numbers from those wonderful intervals, like -3, -1, 0.1, and 1. This will be kind of fun. Now, here's the reason I wrote it factored, because this is generally what you want to do. You want to plug your critical values back into the factored version of the derivative. And make sure it's the fully intact factored version of the derivative. Because sometimes when you set it equal to 0, if you had like a -2 in front, you might divide through by a -2 to get rid of it. But that -2 in the front would be very important for the sign of the derivative, which is what we're after. So what do you get when you plug in a -3? You're going to get a negative times a negative times a negative. 3 negatives make a negative. Oh, there we go. Plug in a -1. You get a negative times a positive, right? Which is negative. And then a negative over here. So a negative times a negative is positive. Plug in a 0.1. You get positive times negative, which is negative. And then if you plug in a 1, you get positive times positive times positive, which is positive. Now, as you work through some of these problems that actually do factor, don't just assume that because you work 3 in a row and they alternate every critical value that's how it actually works. So you can't just say, if the first one's negative, I can just alternate the signs after that, because it could be positive all the way across. You never know. Okay, so now that we have the chart, we're going to use it twice. We're going to use it, of course, to answer this question, which I'm just going to shrink all this work down here, which normally we're not going to have to do. And we'll say that F is, let's do decreasing first. We'll come in from the left. Decreasing on the interval from where to where? -infinity to -2.963. Union what? 0 to 0.337. Yeah. So wherever you have negatives, and again, we're using the critical values at the top as the boundaries. And then F is increasing wherever you have positive signs. So that would be on the interval from -2.963, 3 decimals, to 0, union 0.337 to infinity. So thanks for the help with the numbers, everyone. Ronnie, Jacob, class. So there's part A. Part B now says to determine the x values of any local max and local mins. Just the x values. Okay, well, we get to reuse the chart. Here's what I like to do, and it's optional for you. Negative to positive, positive to negative, negative to positive. I like to draw the smiles and the frowns right there so I can visually see if they're local max or mins. So it looks like we have 2 mins, right? Now, because we have 2 mins and they are mins for the same reason, we can clump those together in one argument. So we could say F has local mins. Are we supposed to say of or at? At, because we're looking for the x values. At x equals -2.963 and 0.337. That would earn a check. And then here's the justification. Since f prime of x changes from what to what? Negative to positive at each of these. I don't really like using pronouns, but if you refer to this here, at here, or this, or these in this case, that's fine because the antecedent is clearly stated. But you want to say it kind of twice. Here's where they occur because that is also where f prime changes from negative to positive. Now that's a local argument. When you say that the f prime is changing from negative to positive at an x value, you're really saying immediately to the left the derivative is negative and immediately to the right it's positive. It's a local argument. And this is the easiest way to get full credit. Now the other one, f has a local max or a relative max, either one, at x equals 0, since instance, what? F prime, you don't even need of x, changes from, and just make sure you get it correct, changes from positive to negative. Changes from positive to negative. Where does it change from positive to negative? At x equals 0. So you could say either at x equals 0 or you could say there, referring back to x equals 0, the location. Either one. But don't just stop after from positive to negative. That's where it exists because that's where the sign also changes. Okay, so that would get another check for the justification on each of those. So that last part is worth 4 checks. All right, there you go. Any questions on that? All right, I'm going to let you start example 4 then before lunch. See if you can do it on your own. Do the same thing. Now notice on example 4, it's asking you for the what? The exact values of any relative extrema. So are you needing to walk away with the y values or the x values? The actual y values. Now it does say to justify, so you're still going to have to say why the maximum y value is the local max and why the local min is the local min. So we have about 5 minutes to lunch. I'm going to let you do that, and then when we get back from lunch, we'll just show the demonstration, and that's just, we'll do example 5 too. So we got 2 examples after lunch, and then we'll be done for the day.